Good morning, everyone. It's a great honor for me to deliver this report. The title is Estimation of the Critical Breaking Load of Pipe Foundations in Soil Liquefaction. Here are 5 parts, so let me start by explaining the background and significance. As we all know, even with modern design guidelines, collapse of pipe-supported structures are still observed after stronger earthquakes, such as the Winter earthquake, New Zealand earthquake, and so on. Over the years, there are so many big earthquakes. The collapse of buildings will directly threaten personal safety. The collapse of road and bridges could seriously harm steel operations, and the collapse of ports and waterways could significantly slow the economic recovery. So extensive structural damage have caused large human and economic losses. Soil liquefaction always takes place due to earthquake. The shaking of the earth causes pressure in the condition of soil, which will make it like a liquid. Soil liquefaction also will lead to several structural failure as well as ground settlement, perimeter cracks, soil sliding, and displacement of foundations. The research works about 5 cases improve the understanding of pipe behavior. From their research, it can be seen that the damage of pipe foundation is merely verified, such as stair failure of bridge columns and pier, and the cable torsion due to uneven settlement, cracks in pipes, and bending and breaking of steel pipes. So why did the pipe foundation suffer such severe earthquake damage in liquefiable ground? Maybe we can find the answer from the Sour Bridge case. This bridge collapsed at about 17 seconds after the beginning of the earthquake, so the main causes of the collapse of the central pipe could not be the inertial force from the structure and the soil liquefaction induced flow. Daher thinks that braking failure was the main causes, so there are some shortcomings in the seismic design of pipe foundation, and the failure mechanism of pipe foundation is not well understood. Okay, now let's go back to the study of pipe foundation failure in liquefied sites. The breathing failure mechanism in liquefied sites is mainly caused by initial load of structure and the lateral load of the floor of the soil. The results focus on the combination of initial load and kinematic load. The results on the braking failure of liquefied sites is less, but the theory they produced the braking failure of pipe foundations through the sensor field test compared to traditional Ola braking with the developer of computer technology. No linear braking has been further developed. So to improve the design code of the design code of the pipe, it's necessary to calculate the critical braking load of pipe, which could avoid the braking instability of pipe in liquefied soil and strong earthquake. In order to Investigator pay thematic response and actual load and lateral load combined axing. A thinking table test is performed. But Terrier advanced the practical braking load is 0.35 times of the Euler's braking load. The three pi tops are equipped with different methods. And the base input motion is a sine wave. So, and we can see it in the figure. The saturated sand layer is fully liquefied under the action of the earthquake. And the timer is equal to 2 seconds, and the soil is full liquefaction. At the end of the test, pi 1 and pi 2 are safe, but the pi 3 is damaged. The direction of pi 3 diameter is vertical to the direction of sticking. The bending moment can be calculated from the recorded strength using the traditional unilaterally beam theory. But the bending moment reached the maximum value in the starting state to liquefaction and then decreased from the experimental results. The maximum bending moment occurred at the pi bottom of the ground surface. From the diameter of the pi 3, failure due to settlement is impossible because the pi bottom is fixed to the container base. The bending failure and bracket failure is possible occur and the axial load and the lateral load action. If the diameter of pi 3 was the bending failure, the diameter could be merely caused by the insular load. Because there are no lateral spring was observed in the test, and the direction of the collapse should be same as that of the initial load. Whereas the observed direction of pi collapse is vertical to the sticking direction. And meanwhile, the possible position of the hinge should be at the bottom of the pi or the soil surface. But the position of the hinge for the pi 3 was found at the point 46 meter distance. So, the maximum moment of the pi 3 is much less than the yielded moment. Therefore, it can be concluded that bending failure is not the main damage in the not the main cause of damage for pi 3. This confirms that the main reason is braking instability. We can say the synchronous ratio and actual load and inclination. The braking failure is the main reason. Since braking instability has been identified as a possible mechanism of pi failure, it's necessary to calculate the critical braking load of pi for liquefied sites. However, the existing calculated method didn't consider the influence of geometric imperfection and nonlinear behavior of pi. In order to solve this, we propose the approach to using the beam no-line Winker foundation model. Firstly, We adopted the full liquefaction PY curve proposed by this, which considers the string hardening behavior at larger strengths. So, we can see it in this figure. As reported by Niedermer, there are two typical initially binding profiles could be used to consider the geometric imperfection, quarter sign profile, and half sign profile. A moment curvature relationship was defined for elastic section, and a gravitational transformation was adopted to consider geometric nonlinearity of pi. The calculation result of the proposed method are good in agreement with the finite element result reported in Niedermer. And the result of a proposed method are in good agreement with the single field test result given by the Bartlett. It can be concluded that the proposed method is reliable, and then an extensive parameter study was performed. Firstly, we studied the effect of geometric imperfection. It is observed that the critical bracketing load decreases with the increasing the initial imperfection amplitude. And next, we studied the effect of rigidity of pi. It can be concluded that the critical bracketing load of pi increases rapidly with the increase of the rigidity of pi. And then we studied the effect of pair height. As can be seen, increasing the pair height decreases the critical bracketing load in all cases. Based on our finding and all of the case, a simplified calculated formula of the bracketing load of pi can be proposed by modifying the Euler's bracketing formula. And the result produced by the formula of pi was consistent with the thin field test result. Therefore, those proposed formula could be used as a simplified calculated method for estimating the critical bracketing load of pi in fully liquefied soil. The following is the Winker-Foundation model based on the expressor during the soil liquefaction. First, the string hardening PY proof was used to calculate the bracketing over the fully liquefied soil. And the next step is going to develop a method for calculating bracketing load, considering the degree of liquefaction. In this method, both the stiffness and the strength of a non-liquefied soil are multiplied by a factor known as the P multiplier. The P multiplier method based on the axial pressure ratio was applied to the model. The mechanical effects such as liquefaction process can be modeled stereostatically. The values of excess pressure ratio in the above method were computed for each soil spring based on a excess pressure profile, representing the degree of liquefaction at a particular instance in time. the degree of liquefaction of the inter-equilibrium soil layer. It is defined as shown in figure, the beta I. The beta I equal to Si divided S. In this study, the centrifugal test data of particular and the kidnap are used to verify the proposed calculation method. As mentioned above, the liquefied perfection is top-down, and the Py relationship corresponding P multiplier are applied to the model. As the liquefaction progresses, the price stopping from L1 towards L8, and the peak loss for its profile of exit pressure decreases. The pi will fill with liquefaction profile L3. It also filled with only partial liquefaction of the soil liquefaction in the centrifugal test. So the property method correctly captures the test result from the table. Thus, we can say the proposed method is reliable. In fact, because the material and the geometric no linearity, there are two cases. One is that the extreme point passes the yield point, and the other is that the extreme point is equal to the yield point. It's necessary to distinguish between the two cases. In the following analysis, it is observed that the pi is susceptible to bending failure at high initial imperfections due to the significant Peter effects. And through the main effect and analysis of various things, the initial imperfection and rigidity of the pi have significant effect on the pi failure models. Through the above analysis, it is recommended that the design of pi foundation be based on the stiff rather than the strength, with low initial imperfection and rigid and axial loading. The following parameter defense is the same as the ruler motion. Missing the above. At the degree liquefaction developed, the critical breaking load decreases. And when the degree of the soil liquefaction is equal to 0.8, the critical breaking load is low. Furthermore, a simplified calculated formulation for the breaking load of the pi was proposed by considering those parameters. The variable W incorporated a number of factors, and then a steel pi foundation of the Star bridge is used in the example. The value of the critical breaking load of the pi calculated by the proposed formula is less than the value of the Euler breaking load when the degree of soil layer liquefaction is 0.8. As shown in the table. Okay, now we will explain the conclusion. First, through the high quality Sticking table test so that a pipe could fail in breaking in liquefied ground, and the presence of the initial load will lower the breaking load. A calculated method of critical breaking load of pi is proposed based on the wrinkle from this model. The bearing capacity of the pies and actual loading was successfully predicted. And then the initial imperfection, rigidity, degree of soil layer liquefaction, and unsupported length ratio and soil relative density have significant effect on the actual bending capacity. In the end, pipe foundation design should be considered the breaking mechanism together with the effects of lateral load. Okay, that's all. Thanks for listening.